Hello and welcome to Weapons of Math Instruction. This is the fifth in my series of videos on uncommon integration techniques, and in this episode I'll be talking about how to use geometric series as an integration technique. As with the other four videos in this playlist, this video is meant for students and instructors of Calculus 2, so I'm going to assume that you're already familiar with geometric series. I'm going to be evaluating the integral in the thumbnail of this video, and here it is right here. The integral from 0 to infinity of x over e to the x minus 1 dx, and I've called this integral I for short. Now, do you see how to do this with standard Calc 2 integration techniques? Because I sure don't. So what on earth would make me think to try to use geometric series as an integration technique on this beast? Well, here's what. This integrand here is almost of the form a over 1 minus r, which is the sum of a geometric series whose first term is a and whose ratio between successive terms is r. The only problem is that the 1 here is in the wrong place in the integrand, but we could fix that easily. And I'll do that by multiplying the numerator and denominator of the integrand by e to the negative x. And if I multiply across, top and bottom, I get the integral from 0 to infinity of x e to the negative x over 1 minus e to the negative x. And now this 1 here is in the right place, as you see here. Now, to make the a in this expression simpler, what I've done here is I pulled this x e to the negative x off to the left, and I'm left with this factor here, 1 over 1 minus e to the negative x. And this factor is the sum of a geometric series with a equals 1 and r equals e to the negative x. Now remember, a geometric series only converges when the absolute value of r is less than 1. So, it's worth noting that e to the negative x satisfies that condition on the interval of integration. So this thing is the sum of a converging geometric series. So in this step, I've rewritten this factor here as this geometric series here, the sum from 0 to infinity of e to the negative nx. And next, I bring this x e to the negative x inside the sum. And in doing so, I combine the exponents negative x and negative nx like so, to get x e to the negative n plus 1x inside the sum. And I can clean this up just a touch. In this step, I've raised the lower limit of the summation index by 1. And in the exponent, I've lowered n plus 1 by 1 to n. And in this step, I've interchanged the order of the summation and the integration. Now, you have to be careful about switching these two operations in general because you can't always do it. However, we can do it in this case because this sum here converges absolutely on the interval of integration. You can check that yourself with the ratio test. Now, this integral is improper. So really, we should introduce a parameter t in place of the infinity and take the limit as that parameter goes to infinity. Now, this integral is easy to do by parts, so that's how we'll take it down. And here are the parts. We'll let u equal x, so then dv has to be e to the negative nx dx. And then we calculate du and v. So differentiating u, I get du equals dx. And integrating dv, I get v equals negative 1 over n e to the negative nx. And here, I've applied the integration by parts formula. And it still remains to do this elementary integral, but that's easy enough. When I do that integral, I get this. So the next task is to evaluate these two brackets. And I've done that here. And then next, we need to take the limit. So when I take the limit of t e to the negative nt, I get 0. And so 0 minus 0 gives this 0 here. And when I take the limit of e to the negative nt, again, I get 0. So I get 0 minus 1, that's this negative 1 here. And if I clean this up, I get the sum from 1 to infinity of 1 over n squared. And this sum should look familiar. This is the sum from the famous Basel problem, which I discussed in the third video in this series. In case you haven't seen it, I'll post a link to that video in the description. So the sum of this series is pi squared over 6. And this completes our example. That's the value of the integral. Thanks for tuning in to Weapons of Math Instruction, and I'll get back at you soon and show you another cool integration technique that you can't find in a calculus book. Bye-bye. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.